Welcome to our lecture on Hamiltonian mechanics, one of the most elegant formulations of classical mechanics. While you might be familiar with Newtonian mechanics, which directly relates forces to accelerations, Hamiltonian mechanics provides a more powerful mathematical framework that is especially useful in quantum mechanics and modern physics. Hamiltonian mechanics is named after the Irish mathematician William Rowan Hamilton, who developed this formalism in the 1830s. It's closely related to Lagrangian mechanics, but instead of working with generalized coordinates and their velocities, Hamiltonian mechanics works with generalized coordinates and their conjugate momenta. The foundation of Hamiltonian mechanics is the concept of phase space. In phase space, we represent the state of a system using both position coordinates, usually denoted by q, and momentum coordinates, denoted by p. For example, for a simple one-dimensional system like a particle moving along a line, the phase space would be two-dimensional, with one axis for position and one for momentum. To derive the Hamiltonian from the Lagrangian, we first define the generalized momentum p as the partial derivative of the Lagrangian with respect to the generalized velocity. Then, the Hamiltonian h is defined as the Legendre transform of the Lagrangian, which is given by the sum of the product of generalized velocities and momenta minus the Lagrangian. Let's illustrate this with a simple example: the harmonic oscillator. For a mass on a spring, the Lagrangian is the kinetic energy minus the potential energy, which gives us L equals 1/2 mv squared minus 1/2 kx squared. The generalized momentum is the partial derivative of L with respect to velocity, which gives us P equals mv. We can solve for v in terms of P, giving us v equals P divided by m. Now we can substitute this expression for v back into our definition of the Hamiltonian. We have h equals p times v minus the Lagrangian. That gives us h equals p times p over m minus 1/2 m times p squared over m squared plus 1/2 kx squared. Simplifying, we get h equals p squared over 2m plus 1/2 kx squared. This is exactly the total energy of the system, with the first term being the kinetic energy expressed in terms of momentum, and the second term being the potential energy. The real power of Hamiltonian mechanics comes from Hamilton's equations of motion. These are a set of first-order differential equations that describe how the system evolves over time. The first equation tells us that the rate of change of the position coordinate equals the partial derivative of the Hamiltonian with respect to the corresponding momentum. The second equation tells us that the rate of change of momentum equals the negative partial derivative of the Hamiltonian with respect to the corresponding position. Let's apply these equations to our harmonic oscillator example. For the first equation, we take the partial derivative of the Hamiltonian with respect to momentum, which gives us p over m, or the velocity v. For the second equation, we take the negative partial derivative of the Hamiltonian with respect to position, which gives us negative kx, or the force. So we get the differential equations dx dt equals p over m, and dp dt equals negative kx. These Hamilton's equations allow us to visualize the evolution of the system in phase space. For our harmonic oscillator, the trajectories in phase space are ellipses, with the precise shape determined by the total energy of the system. Each closed curve represents a different energy level. As the system evolves, the point representing its state moves along one of these ellipses, completing one cycle for each oscillation of the mass. One of the key insights of Hamiltonian mechanics is that it reveals conservation laws through symmetries. If the Hamiltonian doesn't depend explicitly on a particular coordinate, the corresponding momentum is conserved. Hamiltonian mechanics also introduces the concept of canonical transformations, which are special changes of variables that preserve the form of Hamilton's equations. These transformations are extremely useful for solving complex mechanical problems by transforming them into simpler ones. The Hamiltonian formulation is not just an elegant mathematical framework. It has profound applications in many areas of physics. In quantum mechanics, the Hamiltonian operator directly gives us the energy levels of a quantum system, and the Schrödinger equation can be seen as a quantum version of Hamilton's equations. In statistical mechanics, the Hamiltonian helps us understand the statistical properties of large systems. And in field theories, the Hamiltonian formulation provides a pathway to quantizing fields, which is fundamental to quantum field theory. In conclusion, Hamiltonian mechanics provides a powerful reformulation of classical mechanics that emphasizes the concepts of phase space, conserved quantities, and symmetries. By working with generalized coordinates and their conjugate momenta, it gives us a clearer picture of the mathematical structure underlying physical systems. The Hamiltonian approach not only solves classical mechanics problems elegantly, but also forms the foundation for modern theories like quantum mechanics and statistical mechanics, making it an essential tool in the physicist's toolkit.